Welcome to Research Renaissance, presented by the Karen Toffler Charitable Trust. Embark on a journey into the forefront of cutting-edge brain science as we feature insightful discussions with a diverse array of guests, from early career researchers pioneering groundbreaking science to influential voices in investment communities, policymaking, and research institutions. Together, we delve into neurological diseases, their causes, treatments, and the quest for cures. Join us in advancing our understanding of the brain and addressing its ailments. Welcome to Research Renaissance. I'm Deborah Westphal, your host and guide through the fascinating future of the brain. Joining me today is Dr. Andrew Holbrook, Assistant Professor of Biostatistics at UCLA. Andrew is also a 2023 Toffler Scholar. Today, we will discuss how Andrew uses AI and advanced algorithms to better understand the brain and the Alzheimer's disease. So let's dive in. Welcome, Andrew.
Hi, Deb. Thanks for having me.
Yeah, I'm real excited for this discussion. And every time we talk, I walk away with something new. So this is a thrill for me. You have a very interesting professional journey so far. I believe you referenced it one time as a long and windy road. It's kind of started, I guess, with your history, your love of history and languages. You spent time in China as an educator, and now you're pursuing your research through the work that you've done through a PhD in statistics and viral epidemiology. Can you describe more and tell us a little bit about that journey? And, it sounds fascinating.
Yeah, thank you. For me, I've always been interested in kind of systems of symbols. So languages have always been fascinating to me. For me, yes, it's true. During my undergraduate education, I studied dead languages. So I studied ancient Greek and Latin. I also studied German and German literature. So that was always very, that kind of had these two different sources. The first source was I was interested in kind of languages are interesting because they're formal, they're kind of systematic, and yet we use them to talk about real things. And we use them to do really real work, to talk to each other, to communicate. That, moving to the kind of work that I do now kind of makes sense because when I'm doing my statistical inference, I'm using a formal system. This time it's mathematics, but I'm kind of using it to kind of better understand the world around me. And the other aspect to it, I think, is, the interest in history is I've always had this kind of bottom up, I can only understand something if I understand it at its most basic level. And then from there, I can put the pieces together. So my interest in history is it's a strange thing to be born into the universe. And you say, okay, well, where are we? How did we get here? So history and studying it kind of helped me to understand and kind of form a basis for what I do every day and how I understand the universe around me. So a long and winding road, but I see a lot of continuity.
Yeah, that's super interesting. And as you were talking, I was wondering, when you were an undergraduate, did you kind of see the future? And did you see these emerging languages with AI and algorithms? Was that something that was kind of on the horizon as you were, doing your day-to-day, whatever that was?
Yeah, I wish I could say that I did, but the answer is no. I did not see the future. But what happened was my dad is a swimmer. So he does master's swimming, and he still does master's swimming. And he was doing his master's swimming at UC Irvine. And he had a good friend there that he swam with that worked at Google. And he knew that I had just graduated college. He knew that I was either about to leave for China or that I had just come back from China. And he said, and he was a programmer. His name was Sean. His name is Sean. He said, if you enjoy studying languages, then you might think about getting into programming and doing something, like data science. And I said, data science, I don't know what that is, but I've always enjoyed math. So, is there a way of, squaring that circle? So actually, it was just from a kind of somebody who did know, somebody who did see the future, and kind of my being willing to take advice. So one thing that I've kind of always thought is very important is I've always tried to learn as much from other people as I can. So that's just one situation where I said, okay, can I use these things these skills that I have in ways that I didn't think about previously? So I followed Sean's advice.
That's great. So what did you teach in China?
I started out just teaching English as you would, expect, right? So I was teaching English at a high school in China, and that was going very well. But the school that I was at, they, for some reason, and now I'm trying to remember back, for some reason, they lost their math teacher. And I'm not sure why that happened. But let's just say that all of a sudden somebody needed to step up and teach math too. So I ended up teaching math and English at this school, and it was a very enjoyable experience, and I learned a lot from it. And maybe I also even learned that I enjoyed teaching the math more than I enjoyed teaching the English, which maybe also might have guided me on my trajectory back into mathematics and statistics, if that makes any sense.
Yeah, it does. It does. It's fascinating, and it's interesting how these things just kind of happen. They're just doors open, and if you're willing to walk through them, it can lead to a real fascinating journey. The key question that your lab is focused on answering is how do visible changes in the brain correlate to key outcomes in patients with Alzheimer's disease? Can you talk more about, how do you do this? And, what are the components of this effort to try to answer that question?
This is work that I started quite a while ago, and this is work that I was doing as a grad student while I was at UC Irvine. And the key collaboration there has been working with Nick Tustison and Brian Evans. So I've worked with them a while. They have this software that they've developed called ANTS. I'm not going to remember exactly what the acronym is for, but let's just keep it at ANTS for now. But this is some really cool software that features a quite complex imaging pipeline. So what happens is patients, they go to the doctor and they sit in the MRI machine. And what that does is it essentially takes a picture of their brain. And when you have that picture of the brain, then you might actually want to be able to analyze it. And there's a number of different ways to analyze it. So what Nick and Brian have done is they developed some mathematics, they developed a new model, they developed this statistical pipeline and this brain imaging pipeline, which is quite complex. But it essentially says, oh, you're interested in, let's just say, 62 different regions of interest in the brain. And these different regions of interest might be interesting for different reasons. But for those 62 different regions, we can actually give you some measure of cortical thickness. So where that thickness is just kind of a very real, natural measure for how healthy that region is, that brain region is. Right? You could imagine that it being nice and plump means that everything is going well, everything is exactly how it should be, and that if you see that brain region deteriorating, then that should be setting off alarms. So, given their software, given their ANTS pipeline, the question is, well, how do we actually analyze that data statistically? There's interesting questions there, and some of these questions are interesting to doctors, and some of these questions are interesting to statisticians. And some of these questions are interesting to doctors and statisticians. So one of the questions is, well, if we can't actually get in there and look at the brain tissue, then how do we know that the pipeline's any good in the first place? Which is a perfectly natural question. So that's something that I've tried to answer using statistics. And then, of course, the maybe more importantly, I don't know, is the question of, well, can we use this to predict? Can we use the thickness of these different regions to actually predict the onset of dementia or Alzheimer's disease? Can we use it to identify Alzheimer's disease in patients in a way that doesn't actually require a lumbar puncture, for example? So, in a kind of non-invasive way. These are things that I've been very interested in for a while. There's all sorts of interesting structure there that you really have to account for as a statistician. If you're going to be doing your data analysis in a correct way, then you need to account for the fact that, that you're seeing a patient once every 6 months.
So is that what the pipeline is? Is the pipeline the imaging? Because a pipeline, there's flow, right? There's flow through it. There's an in and an out. Is that the images that are being taken across a time for the patient?
Yeah, so the pipeline will take in, so the most basic pipeline will just take in an image, and then it outputs, the cortical thickness measures for the different regions. But then there's these longitudinal pipelines. Because we see the patient again after a certain fixed amount of time, of follow-up time, there's these kind of longitudinal pipelines where you feed in a number of images over time, and then you get some sort of cortical thickness measurements out over time. So the question is, how can we use those measurements that these pipelines are outputting? How can we use those to do prediction better, or to actually learn something new about the trajectory of Alzheimer's?
So this, and I think you're saying cortical
thickness. Yeah, so
thickness. The cortex, right? The thickness. So you can't see that on like normal MRIs right now. It's just a flat image. Is that correct?
Yeah, it's a flat image. So there needs to be some sort of segmentation where it's segmented into the different types of matter, and then you also have to segment the different regions of interest, which can be done historically. This was something that was done by hand by an expert, and nowadays this is done using computational algorithms and actually AI.
So the ANT capability, is that on all MRI machines now, to where if you're imaging the brain, or how pervasive is it across MRIs?
Well, there's a number of competing software that do this. So it's not on the MRI machine, but it is on the computer that is being used by neuroscientists, for example. So yeah, there's a number of competing software that have their own strengths and weaknesses. Ants is one of them. Another very popular one is FreeSurfer. So they're doing slightly different things, and they have slightly different strengths and weaknesses.
Yeah, I was just curious because if people go into a neurologist or into an MRI lab, are they getting this capability, or is this something that only a few get access because of either location or financial type of so? And then you mentioned there's questions that concerning that would from a statistics perspective, and then there's questions that a doctor. Can you be a little even more specific about the statistics side? What is it that is that across a population? Is that across trying to understand the different areas in the brain? And yeah.
Yeah. So from the statistics standpoint, there's a number of different questions that are interesting. So the first thing is kind of like a basic question that I kind of mentioned earlier, which is, how do you know that your data is good if you don't have access to ground truth? And the answer to that question is, well, you don't really know. But if you make some basic assumptions, then you might be able to say that certain data is better than others. For example, if I have, let's just say, for instance, it's broader than this, but let's just say that we have two pipelines. And both of these pipelines, they both have the same inputs, right? These MRI are the inputs. And then they have similar kind of outputs. They're both supposedly outputting the thickness for, a brain region. Let's just say, keep it simple, one brain region. Well, if you feed in the same MRI again and again, and you get radically different results, so that's kind of like a test-retest strategy to figuring out if the data that you're producing is any good, then you would say that, that the pipeline isn't very good because you're getting radically different results every time that you apply it. So there's going to be an issue there. And you wouldn't want to be drawing any or trying to draw any, scientific conclusions from that data. So that's it's an extreme case, but it kind of gives you an idea of how we can begin to approach that question. Then the other thing that's interesting from a statistical standpoint is, statisticians, data scientists, people in machine learning are always interested in structured data. So what does that mean, structured data? It means that there's some sort of time structure, right? So that's the patient coming in every 6 months, right? Where we need to somehow incorporate that into our models in order to actually learn the correct lesson from the data. We actually need to take into account that fact that we have time structure. Then there's also spatial structure, right? We have these different regions in the brain that some are close to each other, some are far away from each other, right? So we also need to account for that spatial structure if we're going to be performing our statistical analysis properly. So those kinds of, when we're dealing with that structured data, then we can, it actually requires us doing something oftentimes that's not a simple, statistics 101 analysis. You actually need to be more creative. So that's a lot of fun for a statistician. And then, of course, it also means that you're actually giving clinicians, you're giving doctors, you're allowing them to learn the correct lesson from the data.
So why Alzheimer's? Because statistics goes across everything. Why Alzheimer's? Why the brain? What is the fascination for you that's what you're kind of dedicating your time to?
For me, Alzheimer's disease is, I think the priority is, or the most important point here is that Alzheimer's is a horrible disease. And dementia is a horrible disease, and we should address them. It's a good thing to spend your time working on, kind of from like a basic human level. So that's the first thing, right? That should be the driving thing, is we can help other humans by addressing this. And then, okay, having said that, it's also just very interesting. And I think that, again, this kind of gets back to what I was saying just a minute ago, which is that this data that we have is, again, it's kind of got this, it's very structurally rich. And we can develop these very interesting models to analyze this data. And it's kind of that combination of both. There's this kind of analytic side to it that I really enjoy. And then, of course, whereas some of my colleagues that I went to school with, they also enjoy analytics, and they're using it to sell things on Amazon. Not that there's anything wrong with that, right? This is progress either way. But what I mean is, it feels kind of like I'm working on the right thing.
Do you have family members or people that you know that have Alzheimer's or dementia or some other kind of neurological disease that kind of is a part of that influence?
Yeah, yes, I do. And I think that, for the purposes of the privacy of my family member, I won't get into that or get into the specifics. But yes, so you see that these diseases are, that there's a human cost, and that there's real suffering involved.
Yeah, and I appreciate that, and I do respect that privacy. I think many of us have seen that, or have been close to somebody that we cared about that have had probably similar kind of experiences there. You mentioned that the data is really important to put it in context that it helps the doctor or the clinician with what they do. Do you work with clinicians, or how do you pass that information on?
Yeah, yes. So I work with a number of clinicians, and most of the time we're working on the research side. So it's kind of the tool development. And the idea is kind of to create a product, a finished product, that then we can take that and we can, incorporate it into general clinical practice. So there's a difference, right? The way that I interpret your question is, oh, am I going over into the doctor's office every day, and saying, looking at that and saying, looking at the image and saying, oh, that one. No, I'm not. I'm not a radiologist, and I'm not a doctor, but I do work with a large number of them in the creation of product. So that's, you create a model, you create an algorithm, you create software, and then you can take that software and you can then go and you can advertise it. You can say, hey, here's a free tool on the internet that you might consider incorporating it into your clinical pipeline, whatever that is.
Yeah, I think it's interesting, and it's not maybe common knowledge that there are clinicians, doctors that are actually researcher. They're the research doctors, and that's what I hear you saying is you're working with them to kind of build the tools to continue that growth of knowledge and understanding. So, what are some of the challenges? You mentioned one of them, which is, just knowing what's going on inside the brain when you can't get access inside the brain as far as a living person. But what other kind of challenges that you have, and can you share any kind of breakthrough moments that you've had that have been really interesting and fun?
Yeah. So the big breakthrough kind of gets back to your kind of an earlier question, which was about the ants pipeline, right? Historically, it's been so computationally intensive. You feed in a number of MRI from a large number of patients, and then you turn the crank. What does that mean, turning the crank? Well, it means that you run you on a large cluster of computers. You run the algorithm for a few days. And then after you've run it for a few days, then you get the results. So one thing that, one breakthrough that we've had on the ants team is that Nick Tustison has developed these ways of using deep learning and incorporating AI into the pipeline itself. And once he's done that, a lot of the computing is no longer required. So you asked a question earlier about, well, is the pipeline on the machine itself? And the answer is no. But with AI actually helping to accelerate a lot of the computing, and the computing is a real rate limiting step here. It really takes a long time. Right? You can't ask the patient to just stay in the office and in the doctor's office for a couple days. But with AI accelerating the computing, then I think that we seem to be getting closer to kind of that real time, the ability of physicians to kind of analyze the data like MRI data in real time. And then once you have that, then you're that much closer to having a biomarker for Alzheimer's, a predictor of Alzheimer's that is non-invasive. There's minimal discomfort for the patient, and you're actually able to make meaningful predictions.
Can you describe deep learning? Deep learning, we hear it. We hear it, we see it in the news and articles. What is deep learning? Because that seems like that's pretty critical to the breakthrough that you're talking about.
Yeah. Uh, so I think that one way to think about it is a function. So, what's a function? Let's just kind of make it as simple as possible. A function is you can think of it as a black box where you put something in and you get something out. Sometimes you put in two different things and you get out the same thing. That's allowed. But what you can't do is you can't put in the same thing and get out two different things. So this is a function. That's all. That's as simple as it is, as it gets. So you got that black box that follows just a few simple rules. So these are incredibly important in mathematics, this framework. And what deep learning does, it gives you this ability to use a computer to approximate any function. And of course, there's all sorts of limitations and special cases and exceptions to this. But in general, that's the amazing thing that deep learning does, is you have this kind of, in math speak, they'll say something like you have a universal function approximator. So that's what deep learning gives you. And once you have that, then you can do all sorts of interesting things in science and machine learning and industry with it. So the other aspect of it that I think is worth mentioning is, that just to kind of, because I'm speaking kind of abstractly here, talking about, functions and black boxes and that sort of thing, just to give, the listener some sort of context, is that actually, while it sounds simple, this is all, the advancement of deep learning and the advancement of AI is all completely relying on engineering breakthroughs and these kinds of engineering marvels that have occurred just over the past, honestly, 15 years. You have the use of these gigantic computer chips called graphics processing units that kind of do these really efficient computations. And then you just combine a large number of them. So I think that there's two ways of looking at it. On the one hand, you can look at the kind of the black box abstract nature, universal function approximator. But then on the other hand, you have to have like this real appreciation for all of the incredible engineering that's gone into the creation of these massive computer chips.
And you also said it's very rule-based, and you have to know the rules, and you have to test the rules, and you have to refine those to get something of value out of the box, out of the function.
Yes, absolutely. Absolutely.
Yeah. And I would imagine that's where a lot of statistics comes into play too.
Yeah, it's honestly, yes, statistics. Like as a statistician, I will tell you that some of the great contributors to deep learning and AI are statisticians by training. We're very proud of this, but at the same time, it's become its own field. It's kind of like it's kind of birthed in statistics and computer science. AI, I mean, is kind of, it's coming from this kind of confluence of statistics and computer science and electrical engineering, and then it's just becoming its own field, and it's really an impressive thing to see.
Yeah, that's really interesting. And you talked about the biomarkers and these predictors for dementia or Alzheimer's. When you think about that and the possibility or the opportunity there, are they? Do you see it as they're very personalized because you can go into the MRI, because you can do this pipeline across a person and across time? And is that then personalized that says your Alzheimer's or your disease is manifesting in this way?
Yes. So the analyses that I have performed are beginning to be personalized. So, when we talk about personalized medicine, we're talking about taking in, vast quantities of data from a single individual, right, to make predictions. So, my statistical analyses that are based on this MRI data. They take into account certain things like genetic biomarkers, for example. Of course, the subjects, the patient's age, the patient's sex, these sorts of things. But that's only the beginning. You're completely right that as we move forward, that there's just going to be a kind of an explosion in the number of predictors, or the number of, in statistics we call them covariates, that just the number of descriptions that we can apply to an individual, to a patient, which will, of course, it should help with prediction, one would think. And that kind of gets back again to the importance of deep learning in medicine over the next 20 years. We're going to just be seeing amazing things happening, and it's really it's fun to be a part of that.
So you talked about some of the technologies and some of the, kind of the advancements that are allowing you to do what you do. Are there other things that kind of just tools, if you would, emerging, maybe it's even processes, or maybe it's just even changes in policy, and are there other things that are kind of helping you?
Yeah, the things that are helpful when you're conducting research is the access to resources, and doing Alzheimer's disease and doing neuroscience research in the United States. It's a wonderful place to be. This is the richest resource ecosystem in the world. It's something that I think that U.S. citizens should be. I don't know how much the average citizen, the average person, knows just how much research is being done in the United States, and just the sheer amount of resources that are being leveraged here in the U.S. And what do I mean by resources? Well, to maintain an ecosystem like this, you need to invest. So the National Institutes of Health, the NIH, invests billions of dollars a year to fund biomedical research, and then there's a number of different agencies in the U.S. government agencies that are investing in research, from the Department of Defense to the Department of Energy, the National Science Foundation. So it's an amazing place to be doing research. Okay, there's that. But then, one thing that I've found helpful as kind of an early career researcher is that's the nomenclature that's often used. As an assistant professor, as somebody who's kind of starting out on my independent research journey, I've found that that private foundations have been kind of instrumental to giving me support, the research. Research support, to giving me the kind of the tools that I need to launch a data science lab. So obviously, as you know, the Toffler Trust has been very helpful to me in getting this research going, and actually in finding other supporters for a project that I've recently begun with a collaborator over at Harvard Medical School. So I think of it as kind of this rich ecosystem, this rich biomedical research ecosystem is kind of being maintained by both government and by private foundations that are investing and that are giving us the tools that we need to succeed and beat something like Alzheimer's disease.
Yeah. You talked about the collaboration, and it's obvious that it's important. How do you, you're collaborating with somebody that's across the country in a different university. I'm sure you're collaborating across the campus at UCLA. Just a couple moments on how important collaboration is.
Collaboration is essential because the things that we're doing are difficult, and it involves a number of different types of science at once, right? We collaborate with engineers, we collaborate with MDs, we collaborate with all sorts of scientists that are doing interesting things that I have no specialty in. I have to rely on their training. So we rely on each other. So collaboration is essential. Now, the actual way that it's done since the pandemic, actually, we've all gotten very good at, I think everybody can relate to this at this point. We've all gotten very good at just having our calls online. And that goes you'd be surprised. It goes, a lot for even my collaborations within UCLA. Oftentimes we're meeting online. Maybe it's not surprising. Traffic in LA is really bad. So, let's skip that part. But yeah, we've gotten pretty good at just doing everything via Zoom or, Skype, as I still call it.
Yeah. Yeah, I call it Skype too. So one in a previous meeting I was with you, there was a discussion around open source. And can you explain, because that would be one of those things that I think enhances collaboration is open source. What is open source and what does it mean to you and why is that important?
Yeah, open source means that the software that we develop, the scientific software that we develop, it's all just patently visible. The code that we've written is visible to anybody that wants to use it. That means other scientists that are working in, just research at universities, or also scientists and engineers in industry can just use our software for free. So that's an extremely important part of when you talk about, I used this term just a few minutes ago, this kind of research ecosystem. Research is expensive, and we all benefit if we can, I'd say, lower the barriers or reduce the number of barriers that kind of stand in the way of all sorts of individuals doing research. There's always going to be a few researchers that have the funds that would be able to afford to lease software to use, some sort of, I guess, if I were to, instead of publishing my software open source, what if I were to instead try to sell it? Well, I might be able to sell it, but in the best case scenario, I'm able to sell it to other people who want to use it. But the problem with that is research is very distributed. The problems that we're trying to answer are very difficult, and we really need everybody to be involved. So I think that open source is important in this way, which is if I can reduce the barriers, if I can limit the barriers that stand in the way, then I can maximize uptake for this particular method that I've developed, for this particular software that I've developed. And if the problem that I'm addressing is important enough, then by reducing those barriers and allowing everybody, scientists all over the world, to use this software, then there's the chance that we can really solve a problem just because we're throwing numbers at it. The more smart humans that are working on the problem, the better, and the more likely we are to overcome it.
Yeah, and it sounds like there is still opportunity for others to take that software and use it for whatever unique kind of tool or capability for a specific where there might be a financial gain for them.
Yes, and that's of course okay.
Yeah, yeah. So what do you wish people knew about the process of research and kind of this search for new understanding that they may not? Because that's what you're talking. Research is difficult. Research is expensive. Research needs, this ecosystem. What else do you wish that they knew about research and what you do that they just may not understand?
I think that I'll build on that and just say that, when we're school children, we learn about Albert Einstein and we learn about Newton, we learn about Pasteur, we learn about all these kind of great scientists. But the truth is that it's teams. The problems that we're trying to solve in modern science are so difficult and they're so complex that it's always these interdisciplinary teams of scientists that really have any chance at all of solving these problems. And then it's not just interdisciplinary teams, it's multiple interdisciplinary teams. that are all, that are trying to solve similar problems, but are taking different approaches to it. So I think that, yes, science is hard, science is complicated, especially science these days, but it's extremely distributed. And when I say distributed, I'm actually using it's a computational term, distributed computing, parallel computing. This is actually the metaphor that I'm using is the exact same hardware that I was talking about earlier that's allowing deep learning to flourish, right? It's kind of this idea that when you have a lot of computing to do, when you have a lot of work to do, you distribute it. You let a bunch of individuals do it. You let a bunch of teams do it. And then somehow, even though maybe a single individual doesn't have what it takes to solve this extraordinarily complex problem, somehow you, as a team and as these groups of teams, and then all of a sudden, as all of humanity striving, we might have what it takes to beat Alzheimer's disease, for example.
Yeah. So I'm going to flip that idea of interdisciplinary, and the question around the pipeline of of people that are getting MRIs. Do you think there's the ability to, when you're looking at the brain now, to get a much more precise diagnosis? And what I mean by that is, for instance, Lewy body dementia gets, misdiagnosed sometimes a lot of times as Parkinson's. We don't really understand ALS. We don't understand aphasia. There's these dementias that we don't know. And there's scientists and researchers that are dedicated, their life to that protein or that disease, or your ability to look at it from, the pipeline of the brain and through different thicknesses and change. Could this also be more of a precise diagnostic tool?
Yes, that's my belief. My belief is that, so I think that even in the next 5 years, we're going to be seeing AI-based diagnostic tools that are taking in, and you referenced this earlier, that are really performing precision medicine and are able to leverage kind of this collection of huge amounts of data from a single individual in order to make predictions. And these predictions are diagnoses and then also prognoses. So both, I'm considering both of these to be predictions that AI-based tools are going to allow us to do. Here, I've been, discussing MRI data and a small number of covariates collected from individual, sex, age, maybe some genetic biomarkers. But we've already moved past that. We're now talking about kind of using these AI-based models to collate and take in just a huge amount of patient data in order to help patients, in order to say this patient has a very specific disease, and more than that, that this is what we expect in 6 months and in 2 years' time.
Yeah, that like we said, the diseases are horrible, but that gives some hope, because time for those patients is not the friend, it is the enemy. And misdiagnosis or running down a path with certain therapeutics or certain types of whatever it may be, it takes up that time. So that precision in the diagnosis of, no, you actually have Lewy body dementia, you don't have Parkinson's, I think would give that patient time to, kind of work the problem versus just diagnosing the problem.
Yes, absolutely.
Yeah.
Time is money.
Yeah. That's, that's very hopeful. Where else do you see, when you look out, pick your time frame, 5, 10 years, what, you kind of shared some of it that you think, what will be happening in 5 years or 10 years. What other things are you really hopeful that we'll be seeing?
Yeah, the big thing that so small picture. So what am I personally interested in is, what we've been talking about, so far is talking about kind of looking at these what we sometimes call like structural brain data. So we're talking about the actual cortex of the brain and looking at that over time and using that to make predictions. But what I'm personally interested in is actually the collection of what we call functional brain data. So this is things like EEG collected data or fMRI. So there we're actually tracking brain waves in different regions. And I'm extremely interested in using and developing advanced AI models to take that kind of data and use that to make kind of higher fidelity predictions earlier on in patients that might have kind of the early signs of dementia in terms of symptoms. And maybe it's too early to actually notice any structural changes, but maybe we can see some sort of functional signatures that allow us to say, hey, we need to actually be keeping track of this. It seems that this patient might be at higher risk to develop dementia. So that's something that I'm personally very interested in. And then, the big picture is this is distributed. Again, science is distributed. And here I am thinking about this specific problem and thinking about the development of kind of these tailored AI models to kind of address this one specific question in medicine. But there's nothing special about me, right? I'm just kind of existing in this ecosystem, and there's 20,000 other data scientists or computer scientists or engineers or physicians that are having the exact same ideas at the same moment. So really, we're going to be seeing some amazing technological advances coming out, and not just AI, but AI in medicine.
Yeah, I would say that you're a little bit wrong there, that there's nothing special about you, even though that you're one of 20,000. That is still a very, very small group dedicated to working these problems. And that's pretty amazing. And Andrew, I think, I appreciate you doing this and spending your time and your energy working these problems, and I'm sure others do too. So that is very special. As we wrap up here, if people are interested in what you're doing or want to collaborate with you, or just want to chat about what you're finding, how do they get a hold of you?
The best way still. It's kind of funny after talking about AI and advanced algorithms and advanced computing. Actually, calling my phone number works well. This is just my number at UCLA. That's 310-794-5423.
We'll drop it in the podcast notes and make sure that people have it, and that's wonderful. So, Andrew, thank you very much, and thank you for going through some of the details here, because it is a very complicated topic, and it's just not only the brain, but what you're bringing to the problem and to the solution to the problem. So thank you very much for going through that and spending your time today. And yeah, it was fascinating. Thank you.
Yeah, thank you for having me, Deb. I really enjoyed this.
Thank you for joining Research Renaissance. For more information and to stay updated, subscribe for more episodes and visit our website at tofflertrust.org. Feel free to call us if you have any thoughts, suggestions, or just want to find out more about the Karen Toffler Charitable Trust. Until we meet again, onward and upward.